Dr. Keshwarjit Singh. He is a co-convener, so it is very unfair, but still from our side also some of us will speak. Is not it? Okay, be brief. Be brief. Be brief.
Okay, sir.
So what I want to say is that in the poster also I told someone give the history of quantum mechanics. There are three equations. There are three fundamental. One is Heisenberg equation in 1925. In the year 2026, the Schrodinger equation. In 2026-27, Dirac shows that Heisenberg equation and the Schrodinger equation are equivalent. Dirac demonstrated so that they stop quarreling after that. In the beginning, Heisenberg and Schrodinger quarrel each other. My equation is right, my equation is right. But when Dirac showed that they are equivalent, they stop quarreling. In 1948, okay, R.P. Feynman, Richard Phillips Feynman, so another approach of quantum mechanics that is called path integral formalism. In 1948, that is what he is going to take.
Thank you, sir, for the nice introduction. Much of my work is already done. Thank you. So it is my privilege and pleasure to present the path integral formulation of quantum mechanics. I am no expert in this field. I am not an expert, but I'll try to do some justice to this area. So this is the video play okay. So this is a short introduction. We are familiar with the conventional quantum mechanics approaches, Schrodinger approach and the Heisenberg approach. As sir mentioned, Richard Feynman, he developed the path integral formalism somewhere around 1948. He was inspired by Dirac again. So this is some key ideas of this approach. So I'll come straight to the point. This is the very famous electron double slit experiment. This was a thought experiment when Feynman first introduced this experiment in one of his lectures, but in modern times this experiment has been performed in the laboratory. So we have an electron gun, a source of electron S and a slit A, and a screen A with a slit here, and then we have another screen C with two slits open, 1 and 2, and we have detectors placed at the final screen B. This is the detector which detects the electrons, and we measure distance of this detector from some reference point, and that distance is x. So for various positions of the detector, we measure the mean number of pulses, that is the mean number of electrons received per second. In other words, we shall determine experimentally the relative probability P that an electron passes from the source to the location x as a function of x. This was the electron double slit experiment. And if we think electrons as particles, then there are two important assumptions. Each electron passes from the slit S and goes to the location x. It must go through either hole 1 or hole 2. As a consequence, we expect that the chance of arrival at the location x is the sum of the two parts P1, that is the chance of arrival coming from hole 1, plus P2, that is the chance of arrival coming through hole 2. Electrons in a hole 1 dagi power x high location se lakpagi probability P1, hole 2 dagi power lakpagi probability na P2. And I'll try to play the video now. So this is the video. Two holes, hole 1 and hole 2, considering electrons as particles. They are being shot from a gun. One hole is closed, hole 2 is closed, hole 1 is open. So this is the distribution of the particles received as a function of the distance. Now we close hole number 1 and we shall open hole number 2. and this is again the distribution of electrons received at various locations passing through the second hole. And if electrons are particles, then when both the holes are kept open, this is the expected distribution, P1 plus P2. So I'll stop the video now and I'll go full screen. So this was the expected result. I'll try to explain this. This was the electron distribution when hole number 1 was open. This was the electron distribution when only the second hole was open. And this was the expected distribution when both the holes were open. But nature behaves in strange ways. The actual distribution is this. The actual distribution is this. It is not D. So the expected result is clearly not the same as curve A. So this was the expected result. This is the actual result. Hence, the experiment tells us definitely that P is not equal to P1 plus P2, or that our second assertion is false. What was the second assertion? The second assertion was P equals P1 plus P2. So the chance of arrival at any location X when both holes are open is not the sum of the chance with just hole 1 open plus the chance with hole 2 open. Actually, it is this complicated curve, and this is a very familiar curve which we already learned from our optics Young's double slit experiment. So it is exactly like the intensity distribution in the interference pattern to be expected if waves, we are talking about waves now, waves starting from S pass through the 2 holes and impinge on the screen B. This is the screen B. The easiest way to represent wave amplitude is by complex numbers. For electromagnetic waves, we normally write the waves as kx minus omega t for one-dimensional waves propagating along the x-axis, where k is the modulus of the wave vector and omega is the angular frequency. So now we can try to state the correct law for the probability P mathematically by saying that this P is the absolute square of a certain complex quantity phi of x, which we call the probability amplitude of arrival at x. Furthermore, phi of x is the sum of the 2 contributions, that is when both the holes are kept open. Phi of x is actually equal to phi 1 plus phi 2, and phi 1 is the amplitude for arrival at the location x through the hole 1, and phi 2 is the amplitude for arrival at x through the hole 2. And phi is given by phi 1 plus phi 2, and the probability is actually the modulus square of this phi, not the sum of the individual modulus squares. And this reflects the wave properties of electrons. So to summarize, we compute the intensity, that is the absolute square of the amplitude of waves which would arrive in the apparatus at x, and then interpret this intensity as the probability that a particle will arrive at x. Now, what if we really try to see whether the electron pass through either of these holes? Electron si hole ani karamba hole phawraga lake and akoina yenge khalagadi. Now we are going to observe. So now we place an observer here, or we place an instrument or any light source here, so that this scatters the electron, and we can detect from which hole the electron actually passes through. So we have a modification here. A lamp is placed behind the screen C, and we look for light scattered by the electron passing through hole 1 or hole 2. And every electron is indeed found to pass by one or the other hole. So when we place an observer and we see, we find that electron passes through either hole 1 or hole 2. But now, the probability of arrival at x is no longer given by the interference pattern. When we actually observe from which hole the electron passes through, we finally get this again. This is when we observe the electron passing through which hole. So when we watch the electron to see through which hole they pass, we obtain the result P1 plus P2, which is given by D. And when we do not watch, we get the interference pattern. So just by watching the electrons, we have changed the chance that they arrive at the final screen. So came Feynman's approach. So Feynman said there are two kinds of alternatives. So he defined two meanings for the word alternative. The first one is, the first meaning carries with it the concept of exclusion. So thus hole 1 and hole 2 are exclusive alternatives if one of them is closed, or if some apparatus that can unambiguously determine which hole is used is operating. So in my earlier experiment, we place a lamp and we determine from which hole the electron passes through. So that corresponds to exclusive alternatives. So if one electron passes through hole 1, it cannot pass through hole 2, if we observe. So that is the principle of, that is what he meant by exclusive alternative. The other is alternative, the other meaning of the word alternative is of interference. It carries the meaning of interference, and we say hole 1 and 2, they are interfering alternatives to the electron when two conditions are satisfied. Both the holes are kept open and no attempt is made to determine through which hole the electron passes. When we do not make any attempt to determine through which hole the electron passes, and both the holes are kept open. And when alternatives are of this interfering types, the laws of probability must be changed to the form P. This is the interference pattern that we saw earlier. This was Feynman's approach. So the concept of interfering alternatives is fundamental to all of quantum mechanics. When alternatives cannot possibly be resolved by any experiment, they always interfere. The amplitude for an event is the sum of the amplitudes for the various alternative ways that the event can occur. This now we use as a fundamental postulate of quantum mechanics, the expansion postulate. And this is the superposition principle. Now let us introduce two more screens with slits. So we introduce two more screens between A and C. E and D, I have introduced two screens, and now I have punched many holes in this screens E and D.
So essentially you have excluded the possibility that the path can turn back.
Yes, for the time being, yes.
For the time being. But there are theories which looks into that as well, right?
Yes. In the sense that part can turn back, it goes through 1, then goes through 2, then comes back through 1 and again. Yes. Okay. Feynman actually says that classical view is actually ruled out. There was Feynman's assertion. I have no idea. Frankly, I have no idea.
I think they have done some experiments which attempts to measure such
Okay.
possibilities.
Okay. So we have introduced two screens with many holes. So several holes are drilled in screens E and D and placed between the source and the screen A and the final position screen B. So several alternative routes are now available for the electron to travel from A to B. So there are I have shown some of the alternative routes. For each of these routes, there is an amplitude, probability amplitude, and the result of any experiment in which all of these holes are open requires the addition of all these probability amplitudes for all the possible paths. Now we increase the number of holes. Let the number of holes tend to infinity. So we continue to drill holes in the screen E and D until there is nothing left on the screen. So E amasung D is a hole nga tanga leitreba. Then there are an infinite number of paths possible through this screen E and V, and each of this path is parameterized by this distance x. And then the next logical thing is to introduce more screens between A and C. So the next thing to do is place more and more screens between the source and hole 1, between the source and hole 1 in each screen, in each screen, and drill so many holes that there is nothing left. So I introduce an infinite number of holes, screens, and I drill infinite number of holes. That means all the paths from A to B, any sort of arbitrary path is now possible. And we continue to apply the principle of superposition until we arrive at the integral over all paths of the amplitude for each path. Then path khudimaki amplitude contribute to final faida. So to come to that, let us try to review our classical mechanics. We have a quantity called action S, and for each path we calculate the classical action S by integrating the Lagrangian. This is the Lagrangian which is kinetic energy minus potential energy of the particle from an initial time Ta to some final time Tv. The particle was initially at xa at time Ta, and finally the particle was at xb at time Tb. And this is the action for a certain path. These are some of the possible paths. And coming back to this one, classical path. Out of these many possible paths, in classical mechanics we learned that the classical path is that particular path for which the action is an extremum. That is, delta x is 0 up to first order. But quantum mechanically, as we discussed earlier, there are infinite number of paths possible between A and B, and each path should contribute. So we have just shown 5 of the infinitely many paths available for a particle to move from point A at a time t to point B at a later time t prime or Tb. And Feynman's assertion postulate was that it is not just the particular classical path of extremum action that contributes, rather all the paths should contribute. And by which amount path singdu contribute kayam tawani? All contribute equal magnitudes. Each of these paths contribute equal magnitude to the total probability amplitude. But not only that, the paths contribute at different phases. Magnitude phase. And the phase of the contribution for a given path is the action, classical action for that path in the units of quantum of action h bar, the reduced Planck constant h bar. So the probability P to go from a point xa at time Ta to the point xb at time t is actually the absolute square of an amplitude k to go from A to B. So what do? We calculate this amplitude, probability amplitude k for a particle to go from A to B, and this amplitude is actually the sum of contribution from each part. It's an infinite number of paths laibanina, path khudimaki contribution the loinamak sum tawa. And since the number of paths is infinite and these paths can change continuously, we have the integration sign here. Yeah, integration over path.
That's not a normal integration.
Yes, that's not a normal integration.
It's a functional integration.
Yes, this is functional integration, where integration is over each path. Okay, so regarding functional integration, let me,
By functional integration, it means for one single part we integrate it and then we take again.
yes, yeah. So, okay.
Not exactly that.
Yeah.
You have so many possible paths, so the integration is over different paths. So the integration is over the paths, not
Yes, not that.
one.
So
So
to
the variable
yeah,
is a path. So normally when you have a function dx, that is the independent variable. Now the independent variable is a path.
it's the path.
One path is an independent.
One very common example that we often miss is action is a functional, not a function. Here, this action is a functional because the domain of action is not a point, it's a path. So a functional is actually a function of a function. Okay. Yes, sir.
Equal contribution
Yes, sir. Face
equal
kenaba.
contribution how we imagine.
I don't know.
that
Frankly, I don't know.
Which will contribute.
Yes.
Aduda, putting up now, equal value will let go contribute to me and man hurry. Can I be hurry? No. But my hurry no. Whether he has borrowed from equipartition theorem in classical physics or randomly he thought. Reason like that.
Sa lay dile mene do hoji idea dile. Okay. So
The black factor to being a side case do not determine.
Hoy. Okay. Okay, loi dore. So this is the transition amplitude, and as sir mentioned, this is actually integration over all paths, all possible paths. Okay. And as we said, each path contributes a phase factor E. And this is the phase factor. This is the phase factor that we have written here. And what is the classical limit? In quantum mechanics, all the paths are possible, but in our everyday life, in the classical limit, we see only one classical path, that is the extremum path. So how do we reconcile these two ideas? The idea is quite simple. The classical approximation corresponds to the case where the action is quite large compared with the reduced Planck constant. S by h bar. Here it is S by h bar. Here it is S by h bar. And S for classical particles, this S is quite large compared with h bar. So that is the reason. So this x bar is the classical path, and if we move slightly away from the classical path, this sinusoidal e to the power I theta is cos theta plus I sin theta, the Euler's formula. This sinusoidal oscillation is so high that that neighboring paths, they eventually cancel out, and what we are left is only the classical path in the classical limit. Cancel chanagi classical path to khaktamak le however, because S by h bar is large. So this is one example. I'll skip this. Feynman actually, this Feynman part integral formalism is actually equivalent to the Schrodinger picture also. Schrodinger equation can be obtained from Feynman part integral formalism, but I have skipped that here. I just like to present, with the interpretation.
But what is the advantage? Is there some advantage of the Feynman path integral?
Yes, sir. These are the advantages, sir. Okay. So connection to statistical mechanics manifests Lorentz covariance and perturbative
So
expansion.
that is useful in the context of thermal field theories.
Yes.
But the other advantage is that, compared to the canonical field quantization, if you can quantize it using the functional integral approach, it can incorporate constraints.
Okay. Thank you.
So it is widely used in conventional physics.
Okay. So I use it in black hole physics. So how do I use in black hole physics? I just 5 minutes. I try to explain my work. Whenever the apparatus is large enough so that classical physics offers a good approximation, the kernel, that amplitude k, is approximately given by, that is proportional to, we have a normalization constant here. That now, here now the action is the classical action. And this is the first image of a black hole actually taken by the Event Horizon camera. This was released in 2019. So this was the first direct detection of black holes. This was the image of the black hole at the center of the galaxy M87. And this is the image of the black hole at the center of our Milky Way galaxy. That we call Sagittarius A star. This is an actual image of the black hole, the supermassive black hole at the center of our Milky Way galaxy. And what is a black hole? I think I don't need to delve into this. Black hole is a very dense, compact object whose gravitational pull is so hard that even light cannot escape. And black hole has an event horizon. Once a particle is inside the event horizon, to come out of that event horizon, the particle should possess speed greater than the speed of light, which is classically impossible. But we have quantum tunneling, so why worry? Even though classically particles cannot come out of the black hole horizon because their speed cannot exceed the speed of light, quantum tunneling is possible. So we apply the principle of quantum tunneling and study Hawking radiation from black holes. So according to quantum field theory, vacuum is buzzing with virtual particle-antiparticle pairs which are constantly created and annihilated. And as sir mentioned earlier, we have the energy time uncertainty principle. And mind you, I like to remind what sir last sir there is no commutation relation between energy and time. We only have this uncertainty principle. So energy can be borrowed for a very short time, particle creation and annihilation. So in the presence of a very strong field or strong gravitational field, the particles, the virtual particle-antiparticle pairs may be ripped apart. If we use the if it is ripped apart by electric field, we have the swinger effect. But if we use gravitational field to rip apart this virtual particle-antiparticle pairs, we have the Hawking radiation. This is the space-time diagram of a black hole. Time axis is the vertical axis, the space axis is the horizontal axis. So we have virtual pair creation and annihilation here. But if a virtual pair creation occurs near the event horizon or inside the event horizon but very close to the horizon, one of the pairs can tunnel out of the horizon and ultimately become the Hawking radiation. To study this, I give a simple example. I'll just finish it in 1 minute. I'll not explain anything. We take for simplicity, we take a scalar particle and we have the Klein-Gordon equation of that scalar particle, the Klein-Gordon equation. And now this metric tensor GAB is no longer the flat space Minkowski metric tensor. This is the metric tensor of the black hole, which is given by this G mu nu. So this is the Klein-Gordon equation in curved space-time in the vicinity of a black hole. And to study the tunneling of particles from the event horizon from such a black hole, we again use the classical limit of the path integral formalism. So conclusion, I'll stop here. The path integral formalism, it provides an alternative intuitive framework for quantum mechanics. It naturally leads to modern quantum field theory and state mech, and it emphasizes summing over histories, giving deep insights into quantum interference and tunneling. These are the references. Thank you.
Anything?
I would be glad to have some comments.
Anything? Still you have 5 minutes.
Masang kitang
Yes, sir.
nasay odan high da nasay gi kanona dirat na second order dakradi nasay gi physical quantity mayam du gi kano do thoraktra vector quantity kargi aduga first derivative la kan di tho I hara ko adurdi haujiki part integral formulation sida nasay gi action nama define tawre ko action do the integrating around the Lagrangian the integrate tawre are Lagrangian definition di khange, but if we see about Lagrange's equation of motion, second order differential equation, but is there any other alternative part integral where the action is defined as the integral of the Hamiltonian?
So
because Hamilton's equation of motion comes.
What happened? Heisenberg equation, Schrodinger equation is based on the Hamiltonian. But Feynman does not did not want to use Hamiltonian. He want to use the Lagrangian. So it is his approach,
Yes.
not Hamiltonian. So
Yes,
he want to use the Lagrangian formalism.
Yes.
And these two gentlemen use the Hamiltonian. So another one, I know more than senior mistake. I went out to
Okay, sir.
Yang interesting was you see black hole ji uri ade haram de uri hara picture ni
Hoy.
picture ni uri and the news the jutu in thene black hole
experimental verification like my conjecture this so
Nothing.
experimental verification
experiment
Nobel Prize winner.
ꯑꯩꯗꯤ ꯍꯥꯎꯀꯤꯡ ꯔꯦꯗꯤꯌꯦꯁꯟꯅꯦ ꯑꯩ ꯍꯥꯏꯗꯣꯏꯅꯤ ꯍꯥꯎꯀꯤꯡ
ꯑꯗꯨ
ꯔꯦꯗꯤꯌꯦꯁꯟ
experimentally ꯉꯁꯥꯏꯒꯤ ꯀꯩꯅꯣ black hole ꯁꯤ photography ꯂꯩꯔꯦ
Lady.
ꯑꯗꯨ photograph ꯂꯩꯔꯤꯁꯦ ꯑꯃꯨꯛ hawking radiation ꯗꯨꯒ ꯃꯔꯤ ꯂꯩꯅꯅ event horizon ꯗꯒꯤ hawking radiation ꯊꯣꯔꯛꯄꯒꯤ ꯑꯗꯨꯅ ꯀꯩꯅꯣ signal ꯑꯣꯏꯔꯒ ꯑꯗꯨꯗꯒꯤ imaging ꯇꯧꯔꯛꯄ ꯀꯩꯅꯣ ꯑꯣꯏꯕ꯭ꯔꯥ ꯉꯁꯥꯏꯒꯤ ꯃꯅꯨꯡꯗꯨꯗ event horizon ꯅꯠꯇ꯭ꯔꯗꯤ ꯊꯣꯔꯛꯇ꯭ꯔꯕꯅꯤ even the light is does not come out ꯑꯗꯨꯗꯤ ꯃꯥꯒꯤ picture ꯑꯃ ꯂꯧꯒꯦ ꯇꯥꯔꯗꯤ ꯃꯗꯨꯒꯤ ꯀꯩꯅꯣꯗꯨꯗ black hole ꯗꯨꯗꯒꯤ ꯀꯔꯤꯒꯨꯝꯕ ꯈꯔꯗꯤ ꯊꯣꯔꯛꯀꯅꯤ ꯊꯣꯔꯛꯑꯀꯥꯟꯗ picture ꯗꯨ ꯂꯧꯗꯣꯏꯅꯦ
ꯂꯥꯏꯠ ꯅꯠꯇꯦ ꯑꯣꯖꯥ ꯏꯂꯦꯛꯇ꯭ꯔꯣꯟ
ꯑꯗꯨ ꯂꯥꯏꯠ ꯅꯠꯇ꯭ꯔꯒꯁꯨ ꯉꯁꯥꯏꯒꯤ optical microscope ꯗ ꯂꯥꯏꯠ ꯑꯣꯏꯗꯅ electron microscope ꯗ ꯂꯥꯏꯠ ꯅꯠꯇꯦ electron ꯅꯤꯗꯅ ꯑꯗꯨ ꯑꯣꯏꯔꯒꯗꯤ ꯑꯗꯨꯒꯤ analogy-ꯗ comparing the optical microscope with the electron microscope microscopy
Okay.
sizinay electron beam ju sizinay adu di event horizon dagi thoriba singdudagi
Okay. So let me try to clarify, sir. The event horizon is inside the shadow region. What we see is outside the event horizon. So outside the event horizon, the event horizon is inside the shadow region. We do not see the event horizon. So the label light chidi sagi gravitational lensing the light to never.
okay
So this light is from sources of.
Hawking radiation is too feeble as yet, not yet observed. Otherwise, Hawking would have got Nobel Prize.
Yes, sir. The typical Hawking temperature is around 10 nanokelvin. So it's quite way beyond the CMB temperature of 2.7 Kelvin. So it is drowned out by CMB.
about 10 nanokelvin near that temperature Bose-Einstein condensation is taking place.
Yes. Yes. So
So, 사기 말 이제 소위들에도 원비에 있고, 만 사이 수마 이기버도,
That's your
수마 이기버도, 수마 이오버,
semicolon.
수마 이오버.
Semicolon.
okay. Yeah.
Lagrangian height.
Yes.
Lagrangian does not depend directly on T. It depends on T through X and X dot. Okay.
Okay. Thank you for that.
CC0 외내봐. 아두가 CD0 외외봐. CD0 외외봐. CD 다.
Sambugi meaning people.
시기제 개념이다. 시기 보통세. 블랙 홀즈 메탈 매म पुलिंग तो ना अन्ना मेटल मैम मागी माना बहुत चिंजिल लगल लापसे इधर मैं चिंजिल दिस नक्शल लगुजे मुझे हिदप तो है अन्ना एक्वेशन दिस से तो एक्वेशन दिस तो सागला कुगी क्या लाइफ
So let us honor him. Even though he's our organizer, main person. Without him, nothing. So he